Hi guys, welcome back. So today we're doing a lightning review of my favorite proof of the entire course, which is this proof that the language ATM is undecidable via a contradiction that involves building a paradox machine. So this is a companion video to lecture 9. If you want to look up this proof, it's on CIPSR pages 207 to 208. My apologies, I put these pages in a previous video where I should have said pages 197 to 199 in the previous, but there'll be a note modifying that. So let's get into this paradoxical proof. What we are proving is that a particular language is undecidable. Remember, decidability means that a Turing machine can look at any string and stop and accept if it's in the language and stop and reject if it's not in the language. So the particular language that we're proving this for is the language of encoded strings that encode a Turing machine and a string such that the Turing machine accepts the string. That's it. So M and W such that M accepts W. And our strategy for proving that it's undecidable, we'll start by assuming for contradiction that it is decidable, and then we'll follow that contradiction. So we'll use the decider that we've assumed to exist. We'll use it as a subroutine to build a paradoxical machine, and that'll be our contradiction. So let's show off this proof. So let H, I suppose I'll write my assumption formally. So I'll assume ATM is decidable, and let H be a Turing machine that decides ATM. So by the definition of decidability, H takes in a string and it accepts if the string has the format above and rejects if it doesn't. So H on the input MW accepts if and only if M accepts on W. If M runs forever on W, H of MW will reject. Likewise, and here I'm just specifying a little bit further for one very specific input, H of M run on its own description accepts if and only if M of M accepts. So what have I done here? Well, we've assumed some encoding that lets me write down a Turing machine as a string on the input alphabet of H, right? H takes in M and W. It lets me interpret some encoded Turing machine. That encoded Turing machine is just a string in the alphabet that H can recognize. So that encoded string can be the string W. So this is asking me to run a Turing machine on a particular string that just happens to be the description of itself. Nothing paradoxical here. I'm just saying, well, run M on this particular string, run this program on its own description. What happens? And we'll call this statement *1. H of M on M accepts if and only if M of M accepts. So now we'll define a new decider P for paradox that works as follows. So P will do the following. On the input, which is an encoded Turing machine, it'll first check that M is a Turing machine, and then it will run that Turing machine on its own description. Excuse me. We don't want to do that. We want to use our decider so that this is a decider. It runs in constant time. So we will simulate H. We'll run H on M of M. H is a decider. So this process will always stop. It'll either accept or reject. And output the opposite of H. So I'll call this particular behavior *2. So why is this well defined? Well, we know we can simulate a Turing machine. We can simulate the Turing machine H. We've also assumed that H is a decider. So H run on any string either accepts or rejects. It'll stop. So our simulation stops, and we can see what our simulation outputs, and outputs the opposite of it. So that's how P works. And now, here's the concluding paradoxical step. Now, consider running P on the description of itself. So P takes an input, which is a Turing machine, and there's a couple of possibilities. So P will simulate H of P run on its own description. That's just by definition what P does. If H of P, P accepts, P of P rejects. If H of P, P rejects, then P of P accepts. Now, why is this a problem? Well, we've already specified that H of a machine on itself accepts if and only if M of M accepts. So this is equal to the statement that P run on itself accepts. And this is equal to the statement that P run on itself rejects. So now we have a machine that works as follows. Running P on itself accepts if it rejects. Running P on itself rejects if it accepts. Both of these behaviors are paradoxical. Neither is well-defined, neither is possible. So this is a paradox. Fortunately, it's a paradox based on an assumption. This paradox results because we have assumed that there is a decider H for ATM. So this is a contradiction. Thus, ATM is not decidable. We've seen what happens if we assume it's decidable. We end up with an impossible conclusion, so it must not be decidable. Now, in absolute terms, it's not a long proof or a very complicated one, but it is mind-bending for humans. I suggest if you're still struggling to understand what's going on here, focus on these 3 lines right here. So this particular thing depends immediately on statement 1, follows immediately from it. The behavior of P follows immediately from statement 2. And that's precisely the paradox. Walk yourself through that, and you'll understand what's going on in this wonderful but slightly brain-melting proof. Now, I hope you enjoyed that. Thank you for watching, and I will see you in class.